Imagine a glass slipping from a table. It falls, it hits the floor, and it shatters. In our everyday world, objects obey strict, predictable rules, existing in a single, definitive state at any given moment. This absolute certainty is the bedrock of classical computing. For decades, we have translated information into a rigid language of binary bits, where every piece of data is definitively recorded as a 1 or a 0. Modern technology exists because we learned to line up those ones and zeros into long sequential chains. We progressed from room-sized machines reading physical tape to the smartphones in our pockets using this same predictable logic. Today, those same rigid rules have become the primary bottleneck holding us back from the next stage of innovation. Deterministic logic has hit a hard computational wall. Solving the next generation of problems requires a complete shift in how we process and structure information. Creating a new chemical catalyst, or a life-saving drug, requires simulating molecular behavior, a task where adding just a few atoms causes the interacting variables to multiply exponentially. Classical computers attempt to solve these problems through brute force, tracing every possible interaction one after another in a linear sequence. Calculating every permutation within a growing molecular web would take today's most advanced supercomputers thousands of years to finish. Overcoming this delay requires us to abandon classical logic and cross into the microscopic realm of the subatomic. Zooming in to the scale of individual electrons and photons reveals a place where the predictable rules of our macroscopic reality completely vanish. Subatomic particles exist in a superposition, occupying a fluid combination of multiple possible states simultaneously. They only settle into a single definite reality when they are actively measured. Erwin Schrödinger illustrated this indeterminacy with his famous thought experiment, a cat in a sealed box that remains simultaneously alive and dead until the moment someone opens the lid to observe it. This world is further complicated by entanglement, where two particles become so inextricably linked that the state of one instantly determines the state of the other, regardless of the physical distance between them. Early physicists were baffled by these behaviors. Albert Einstein famously questioned the validity of entanglement, dismissively calling it spooky action at a distance. We now recognize these phenomena as the universe's native operating rules, a hidden logic that we can finally exploit for computation. This realization led to the development of the quantum bit, or qubit, which replaces the binary bit as the fundamental unit of information. A qubit uses superposition to represent a 0, a 1, or a weighted combination of both at once. This allows a processor to hold and manipulate vast, multidimensional computational spaces. To navigate these spaces, quantum algorithms rely on interference. Imagine a maze where probabilistic waves flow through every corridor simultaneously. Troughs collide to cancel out incorrect paths, while peaks build to amplify the correct, measurable answer. Quantum computers solve problems by physically mimicking their internal structure, allowing incorrect answers to eliminate themselves through the natural flow of interference. Harnessing this power requires overcoming a massive engineering obstacle known as decoherence. Any interaction with the outside macroscopic environment, stray heat, noise, or even light, causes the delicate quantum state to collapse instantly. Maintaining stability requires supercooling systems that plunge processors to temperatures 100 times colder than the vacuum of outer space. Even in these extremes, stray errors occur. Engineers use advanced error-correcting codes to pool the resources of multiple physical qubits, maintaining a single, stable point of data. Success in the quantum era depends on isolating the subatomic world, shielding it from the noise and chaos of the macroscopic reality we inhabit. We have already reached the milestone of quantum utility, where quantum hardware can accurately run circuits that are impossible for classical machines to simulate. The next horizon is quantum advantage. Hybrid systems will soon solve complex chemical and logistical problems significantly better and more efficiently than any classical method in history. We have moved past simply observing the strange boundary of reality. We are now engineering with its native language, applying the deepest laws of physics to compute the future.